We resume the morning session with Paolo Perrone. He will talk about CAN extensions and partial colimits.
Thank you, and thanks to the organizers for managing to organize this. It's very reassuring to have events like this in person again. And I have to say, it's also very reassuring to see these events happening in my home country. So I'm going to talk about CAN extensions, and the title is pretty self-explanatory. It's a joint work with Walter Tholen. We started working on it while I was with him at the York University. So what's the idea? What is a way you could explain to a new student of category theory what is a left CAN extension? In some way, it's like replacing parts of a diagram by their colimits, like in some way. So maybe let's start with an easy example. Suppose you have a category that looks exactly like this and form a diagram of this shape in C. Okay? Now, suppose that you have a functor that identifies these two objects into one and so on, and now form a CAN extension. Okay, so a CAN extension, first of all, is a diagram that picks out something like this indexing category there. And it comes with a two-cell, which here will give arrows in this form. Now, sometimes, such as in this case, these arrows form a colimit cone. This is particularly the case whenever F is an up vibration, a split up vibration. But not always. But in some sense, what this CAN extension is doing is replacing these parts of the diagrams by their colimits. Okay? Now, in easy cases, this happens on the nose, but if F is a generic functor, it's not quite like that. So you don't really have like pieces of diagrams that are this definite. First of all, because they may be infinite, but also sometimes it's more like slices of this diagram. So it's a little bit more complicated, but in some sense, these are still parts of a diagram. How can we make this mathematically precise? Okay, so for those of you that were at CT in Ponta Delgada, I've already talked about a way of encoding expressions and how you can evaluate it partially as opposed to totally using monads. I was doing that on sets and on like measurable sets at the time. So let me recall, if you have monads, say on set, but of course you can use other categories too, then you can see a monad as a way of encoding formal expressions, possibly infinitary. Okay, so if you have a set with these elements, then say the free commutative monoid monad can be seen as forming formal sums of elements of these sets. So what is x1 plus x2? It's nothing, doesn't have a result. You just write it like that, formally, okay? You can write like triple expressions, you can write single elements, these are the ones that come from a unit, and so on, okay? And monads are like iterative, so you can form, so to say, formal expressions of formal expression, meaning that this thing is a formal sum of these blocks, which are themselves formal sums. But the plus inside the box is not the same as the plus outside the box, and they don't talk to each other, okay? So you probably know the multiplication of the monad delays these boxes so that the two pluses get to talk to each other, okay? All right, so algebras are places where instead these are not just formal, but these things can be evaluated. So 2 plus 1 is not just this expression written like that, but you can say that it's equal to 3, and that's the structure map of the algebra. So all monads on set can be interpreted this way. Of course, operations may be infinitary in general, okay? All right, so now I want to say that this thing can be partially evaluated with this other thing. How do you do that? Well, ideally, you have to say that in some sense, you first do this thing here on the left. So here's the definition. If you have two elements in TA, so sums of elements of the algebra, okay, but still at the formal level, then this can be partially evaluated to that if there's an element in here in the preimage of mu. So mu was removing the boxes, okay? So an element that mu evaluates to here, meaning a way of putting boxes in this expression, such that if you apply TE, so T means do whatever you have here term-wise, E is evaluate, so evaluate termwise. So evaluate the boxes, you get the second thing. Okay. So basically, if there's a way of grouping the things in here such that evaluating the groups gives you the second thing. Remember what we were doing before with diagrams and colimits. All right. And so that's the rigorous definition. It works for every monad. Of course, it doesn't have to be on set if you take generalized elements. And for those of you that are into like a higher category theory, if you want, these are the one cells of the bar construction of the monad, or if you know lax codescent objects, these are pretty much the things that are connected by an arrow when you form the lax codescent object. So we will not use monads on set. We're talking about colimits, so we have to be in cat, where these are locally small categories, possibly large. And the monads in questions that include colimits are, of course, the free co-completion monads, which I'll talk about in a moment, but mostly the monad of diagrams. Okay, so I did not make this one up. It already existed. Monads form, so diagrams form a monad. So maybe let's see how this works. So first of all this work is conceptually not particularly hard. The hard part is taking care of size issues, because we don't just want to do pre-orders, so we have to make sure that all these colimits exist. So a diagram is small if it's indexed by a small category. What is a morphism of diagrams? Okay, so we have two diagrams. So a morphism of diagrams, so these diagrams have different shape in general. So you have a functor translating into the shapes and the natural transformations here, okay? So it's not just natural transformations between the diagrams, but the new diagram may have new objects and new arrows that were not present in there. So it's not just deforming the diagram into a new diagram, it's deforming the diagram into possibly a sub-diagram of the new. This category is still locally small if C is. And so we have an endofunctor, which is part of a pseudomonad. So I will say monad throughout the talk, but I always mean pseudomonad, so fully weak to monad, okay? And I'll also be sloppy on like the 2 and 3 cells. What is, well, okay, you can probably imagine what the unit of the monad is the one object diagram. The multiplication is more interesting because it's a growth and deconstruction. So take a diagram of diagrams. So take basically a diagram in the category of diagrams. So this is a morphism of our indexing category, J, that will be more like this. So for this object, we get a diagram in C. For this other object, we get this other diagram in C. And now the growth and deconstruction will mediate this cell. So to say, incorporating all these diagrams into C into one big indexing category, where the objects are the unions of all the objects of these categories, still small union of small sets. And so here we got a new diagram. And so that's the way of forming the objects in here. So co-complete categories are pseudo-algebras of this monad, the pseudomonad. So this in particular, the multiplication diagram is a way of decomposing colimits, which also appeared in another work by Walter Tholen. Some of you may have seen it. So when I see co-complete categories, first of all, I mean locally small categories with small colimits. And also, technically, the colimit of a diagram is not really a thing. It's an equivalence class. So every structure map of the algebra is a choice of a colimit for each diagram. Every choice will make these things work. And every choice will uniquely determine the 2 cells and make this diagram commute up to, well, such 2 cells. Okay? It's also important to say not all pseudo-algebras are in this form. So this is not the free co-completion monad. Some algebras are in this form, which are the ones we care about. There's other ones, for example, the free ones, like DiXC is obviously itself an algebra and it's not in this form. Okay. All right. Let's now try to go towards free co-completion. And we want to first, so we have a diagram, and we want to take not quite its colimit, but just like before we were taking formal sums, we want to take formal colimits or free colimits. So what do? We take the unit embedding, and we take the colimit in the category of presheaves. Or if you want, post-compose the unit embedding to our diagram, and now here you take the colimit, all right? So you know, like presheaves and the unit embedding are like free co-completion, so they add colimits freely, and we take that colimit, that free colimit, not the actual colimit. And it's in general they don't coincide, right? So the unit embedding preserves colimits only when they're absolute. So in general, these things are not the actual colimits; they are like formal, so to say. Okay, and I call this construction the image presheave. By some analogy with probability theory that I explained at the end. If this thing has already a name, I will be very happy to know. I couldn't find it in the literature, but maybe it's just me not looking hard enough, right? But you have to interpret these as free or formal colimits of a diagram. Also keep in mind, we want small diagrams, so these are very particular presheaves, which are not just colimits of representables, they are small colimits of representables. So these are called small presheaves, and that is crucial. This is crucial. So what can we say about this image presheave construction? So the first thing is that they kind of refine the theory of cofinal functors, which we call confinal here. Maybe see the paper for why, but it's those functors that always preserve colimits when they exist. So if we have two diagrams, you see, having the same image presheave is a bit like stronger than having the same colimit. So the following conditions are equivalent. First of all, they have the same image presheave, the same free colimit. The second thing is, not only do they have the same colimit when they exist, but if you post-compose with every functor, then the colimits will also agree after applying such functor. Again, if there exists. The writing here is a bit sloppy. What I mean by this is one colimit exists if and only if the other one exists, and in that case they are isomorphic. Okay? And the third thing is they are connected by a zigzag here, where all the arrows of the zigzag are cofinal functor, and all the categories appearing are small. So the usual theory of cofinal functor is the equivalence of 2 and 3, pretty much. And well, going from 2 to 1 is also pretty easy. Take F to be the unit embedding. The bulk of the work is going from 1 to 3. But so this gives you an idea. So we call these functors mutually confinal, and it means that they have the same colimit in a very strong way. So in such a way that is closed under post-composition. Also, this generalizes the theory of absolute colimits, because now let's take K to be in one object category, so that this is just an object, and our statement becomes, having the same image presheave means that this has a representable image presheave. That's equivalent of saying that X is the colimit of D, and such colimit is preserved by every functor. And the third condition, that's a bit harder to see. So we were saying that was a zigzag and so on. If you do it for just one object, that just reduces to having a cone, which we'll know will be a colimit cone. And this cone has an eventual section. So the arrows into X eventually will be split. And this split is essentially unique. So, and you probably know this is the characterization of, equivalent characterization of absolute colimits. So this can be seen as a special case of this idea of image presheaves in this theorem. Okay, so small presheaves, so the ones that are arising in this way, form a locally small category. So again, we have an endofunctor, and this endofunctor is part of a pseudomonad, which is a free co-completion monad. I mean, two monad, of course, pseudomonad. So again, let me stress, it's not a relative monad. I mean, not just, it's really a two monad. We don't have size issues because we're taking small presheaves. So some people say Like the presheaves are the large co-completion, which is not really like functorial in some sense. This one is, because we just want small colimits. So if you just restrict to small colimits, which usually are the one you care about anyway, usually, then nothing breaks, okay? So the algebras now are really co-complete category with choice of weighted colimits, which we express as coends. So if you have a small presheaf on C, then you obtain an object of C by taking the weighted colimit of the whole category weighted by the presheaf. In a moment, I'll tell you why this exists, even if C is large, okay? So if you're confused by this thing, but if you, like me, are less confused by measure theory, compare with what happens in the case of probability monads, where you have a probability measure, and the algebra structure map of an algebra takes a probability measure and gives you, so to say, the average, the expected value, the center of mass, like position weighted by how much stuff there is at each position. So this is like in physics, this is the center of mass. In probability, this is the expected value. This is exactly the same, mind the difference in order, okay? This is not the tensor of monadal categories. This is the copower, the one weighting this column. Okay? So there's a very deep analogy between these two. More on that in a moment. Why does that colimit exist? Well, first of all, P is small, so there is a diagram of which that thing is an image. And so we just plug the image in there, and by the co-unit dilemma, this colimit exists if this one is and there is more. Moreover, this derivation tells us that, as the slogan says, the colimit is the same thing as the coend of the image presheaf, which is basically saying that image mediates between the two monads, or like this map that takes, a diagram and forms its image presheaf is a morphism of monads, the weak one, okay? So if you want, that's the reason, or maybe we should say that's how co-complete categories are Dioc algebras too. Because co-complete categories are exactly the algebras of P, and we have a morphism of monads, so we have here something a bit like the restriction of scalars, just higher dimensional. Okay. All right, let's go towards the main statement. So recall partial evaluations. We're having something in TTA, which was this like grouping of the first expression into the second. Now we want to do this for image presheafs, and we just copy the definition. So take an algebra of P, so a complete category, and take two small presheafs. We say that Q is the partial colimit of P if you do this, but with colimits. So basically, if there exists an element in PPC such as mu and so on. Okay. And now here comes the main theorem. So Q is a partial colimit of P if and only if you can write P and Q as image presheafs of diagrams which are in a can extension situation. So P can be partially colimited, let me say, to Q if and only if P is the image of some diagram such that if you take the can extension of the diagram along some functor, then you get a new diagram whose image presheaf is Q. So at the level of image presheafs, you have partial colimits. At the level of diagrams, you have left can extensions. Let me say these are small, this is co-complete, so these are pointwise. Okay, always pointwise in this talk. Now let me also remark, F is not an up vibration in general, okay? That statement, which is much easier, does come into the proof. It's like the first step, and it turns out to be the statement that you get for the Diag monad. So Diag partial evaluations correspond exactly to can extensions along split off vibrations. So that's the, so to say, the easy case, the also one that I gave at the beginning of the talk. The general case has arbitrary functors is much harder to prove because you have to translate between the two monads in such a way not to break size issues. And that's really like where the dirty work comes. So making this stable under size issues, basically. And that's really where the work comes in, okay? So that's the main statement. And why was I interested in this? I was interested in this because there's an, I would say, equal statement in probability theory. That says the following: let A be a Banach space. I think you can do it more generally, but I could do it for Banach spaces. So I talked about this in Ponte Delgada a few years ago. So there is a partial evaluation of probability measures, so partial center of mass instead of colimits, if and only if, again, instead of diagrams, you have random variables, and instead of Khan extensions, you have conditional expectation. So before, partial colimits were corresponding to taking a diagram and forming the left Khan extension along this morphism. Probability, you have random variables and forming the conditional expectation given this map. Now, for those of you into measure theory, usually you do conditional expectation with respect to sigma algebras, not functions, but what I mean is the sigma algebra given by pulling back along this measurable map. Okay. So this diagram does not commute, just like the Khan extension one doesn't, but in some sense, it's the best approximation into having a commutative diagram. So to conclude, if integrals are a little bit like weighted colimits, so hence the notation, like coends are usually written like integrals, right? And a lot of things are analogous. This work is adding 3 more lines at least to this table. They're saying that random variables are basically like diagrams, image measures are like image presheaves, hence the choice of the name, but mostly that conditional expectations are like Khan extensions. So if you want, if coends are like integrals, then the conditional expectation of categories is the Khan extension. All right, I think I'll stop here. Let me just say, you can find this in this preprint. More about partial evaluation can be found in the first 2 papers. The probability theory case was in my thesis, and some related work by Walter Tholen about decomposing colimits is here. All right, I'll stop here.
Thank you. Are there questions? We're going to open your mic.
Hi, Paolo. Very nice talk. So just to comment on your image presheath construction, perhaps you already know this. So you probably know the comprehensive factorization system, the comprehensive factorization of a functor, which factors a functor into a cofinal functor followed by a discrete fibration. So if I understand correctly, this image presheath is precisely the presheath corresponding to that discrete fibration you get in that comprehensive factorization, which to me suggests that image presheath is a good name for it.
Oh, okay, great. Yes, in the small case, it's exactly the one you get from the comprehensive factorization.
Mm-hmm.
Yeah.
Okay. Yeah. I guess there must be some kind of size business going on.
Oh, thank you.
Adriano.
Hey, thanks, Paolo, for your talk. What are the actual algebras or pseudo-algebras for the monad, the diag monad that you said examples of them were co-complete categories? Do you know what the general algebras are as well?
No, I don't. And I wonder too. So I feel like probably categories that admit lax colimits of some kind, like the growth and deconstruction, seem to be algebras too, but I don't know if that's exhaustive. And yeah, so if anybody has ideas about that, like what are all the algebras of the diagram monad, I would be interested myself to know. I don't know. It's a great question.
Okay, thanks.
Any more questions? There's a question up there.
Hi, thanks for the talk. My question is the table you showed in the last slide somehow formal, or is just an intuition for now?
So if you're asking whether both are instances of something, Well, I can say yes of a monad, I guess, a commutative monad. I know that's not satisfactory. What is true, though, is that theorems between the different entries of the table work one way and the other way. So, for example, you have this thing that, I don't know, every small presheaf is a small colimits of representable ones that correspond to the fact that every measure is a possibly infinite convex combination of Dirac deltas, which is Choquet's theorem, well, part of Choquet's theorem. Then you have, and things like that. So it's not just, so to say, a convenient picture, but theorems on one side give you theorems on the other side. Making those instances like formally of something, which goes like beyond analogy and beyond just saying those are both monads, is something I would be very interested in trying to do, but so far I couldn't. Maybe Markov categories could like come for help in that, but again, I don't really have anything rigorous to say. But yeah, that's again a great question. I wonder too.
Are there any more questions? If there aren't, then let's thank Paolo again, and we'll reconvene in an hour.